Hello, geometry students. In this unit 7, we're going to be talking about similar polygons. We've been talking about congruent polygons for a long time, but in this unit, we'll be talking about similar polygons. And so before we define what a similar polygon is, we first need to talk about ratios and proportions. So I think most of the first part of this lesson will be a review for you. So let's start with what a ratio is. A ratio is the comparison of two quantities or two numbers using division. The ratio of A to B can be written in three different ways. Sometimes you'll see it written with a colon. You'll see A colon B. That represents the ratio of A to B. Sometimes you'll see the word 2, so it'll look like this, A and then the word 2B. But in a math class, the most practical way to represent a ratio is as a fraction. So it would look like this. A is the numerator and B is the denominator. Now, please take note that B obviously cannot be equal to 0, or that ratio or that fraction would be undefined. Okay, ratios are usually expressed in simplest form just because if they're in simplest form, they have the most meaning. So for example, if you hear that, let's say there's 32 players to 18 sponsors at a camp. So let's say 32 players to 18 coaches at a camp. If we reduce that ratio and reduce it down to 16 to 9, that just gives us a little clearer picture of what's going on. 16 athletes to 9 coaches. That's almost a 2-to-1 ratio. So simple, when you have a ratio and you put it in simplest form, it's just going to have a little bit better meaning to you. It's not incorrect if it's not reduced, but it'll mean more if it's in simplest form. Okay, sometimes we'll see extended ratios like this, like A to B to C, okay? That's when we're comparing 3 or more quantities. So let's take a look at it at where we might use an extended ratio, like in this example. The ratio of the measures of the sides of a triangle are 2 to 2 to 3, and the perimeter of that triangle is 392 inches. So the question is, what are the lengths of the 3 sides of the triangle? Now, it's important to realize that 2 and 2 and 3 are not the lengths. Obviously, if the perimeter is 392, remember the perimeter would be the sum of those 3 sides, and 2 plus 2 plus 3 does not equal 392. But if we knew what those 3 measures were, they would reduce to 2 to 2 to 3. Now, when you reduce, just like when we reduced this 32 to 18 down to 16 to 9, we found a common factor and divided it out. In this case, that common factor was 2. Well, we don't know what the common factor is. So since we don't know what that common factor is, let's just call it x. So again, our measures of the 3 sides of the triangle are not 2 and 2 and 3. That doesn't make sense, because 2 plus 2 plus 3 does not add up to 392. But if we multiply all of them by that common factor of x, those 3 expressions would total 392. So we're just going to write the equation that 2x plus 2x plus 3x equals 392. Now we can solve that. So what would that be? 7x equals 392. And if I divide both sides by 7, then x is 56. So now I know that my common factor is 56. So to find the 3 sides of the triangle, I'm going to multiply 2 and 2 and 3 by 56. So 2 times 56 is 112. So 2 of the sides would be 112 inches. And then that third side, when we multiply 56 by 3, would be 168 inches. Okay, so you'll see some problems like that in your homework. So just remember that this example is here. All right, so we've talked about a ratio. A ratio compares 2 quantities. Now, a proportion is an equation that states that 2 ratios are equal. Okay, so if I have a ratio of A over B and a ratio of C over D, if they are equal, we call this whole equation, we call it a proportion. Now, there's some parts of a proportion that you may have learned before. The 2 along this diagonal, those 2 values are called the extremes, and the other 2 values are called the means, okay? And this is a fact that you probably have learned in the past, and that is that in a proportion, the product of the extremes is equal to the product of the means, okay? So if I have A over B equals C over D, where B and D are neither equal to 0, then the product of the extremes, remember the extremes are along this diagonal, so A times D is equal to the product of the means. The means are along this diagonal, so we'll take B times C. All right, now, what you have probably heard in the past, and what we'll probably use a lot, is that, in other words, the cross products of a proportion are equal, okay? So whenever we have a proportion, those cross products will be equal to each other. So we can use that fact to solve some proportions when there are unknowns involved. So let's look at these examples. X over 4 equals 11 over negative 6. We can use the fact that the cross products are equal to each other. So if I multiply the extremes together, I would get negative 6x. And then that product will be equal to the product of the extremes, 4 times 11, which is 44. And then we'll divide both sides by x. We'll get x equals negative 44 over 6. And then, of course, we could reduce that. So x would be negative 22 thirds. Or if you wanted to, you could turn that into a mixed numeral. But really, you don't need to. The negative 22 thirds is just fine. All right? Okay, example number 2. Let's cross multiply again, but this time you need to be careful because notice that one of the parts of this proportion is a binomial. Whenever you see more than one term, do yourself a favor and put parentheses around that because that will remind you that when you cross multiply, you need to use the distributive property. We're going to have to take negative 4 times 2y and negative 4 times 5. So when we do, we would get negative 8y minus 20 is equal to 42, and now we can solve, is equal to 42 because the other cross product is 7 times 6, and so those cross products are equal to each other. So now we'll solve for y. I'm going to add 20 to both sides, so I'd have negative 8y equals 62. Divide both sides by 8 by negative 8, and we would get that y is equal to negative 62 eighths, or that would reduce to negative 31 fourths. Or if you prefer it in as a mixed numeral, it'd be negative 7 3/4, but there's no need to do that. You can just leave it as that improper fraction. Okay, let's do one more. When I cross multiply here, I see that we have 2 binomials. So let's go ahead and put parentheses around those binomials so we'll remember that when we cross multiply, we need to distribute. So I need to take the 7 times the z and 7 times 4. And when I do that, I get 7z plus 28 is equal to, now let's cross multiply the other way. Again, take 9 times z and 9 times negative 1. So we would get 9z minus 9. Okay, and now let's solve that for z. Now I see I have a z term on both sides. I just want one z term on one side. So I'm going to subtract 7z from both sides. And I would have 28 equals 2z minus 9. Then I'm going to add 9 to both sides, and I'd have 37 is equal to 2z. Divide both sides by 2, and we get that z is 37 over 2, or if you don't like that, you can call it 18.5. All right. Now, in this unit, we're going to be writing and solving lots of proportions. So I want you to take note of the following. The following proportions are equivalent, and we're going to verify this by comparing the cross products. So if I cross multiply, let me just grab a highlighter here. If I take the cross products, I would have AD times BC. Okay, let me just jot that down. AD, oops, let me do that with a pen, sorry. I'd have AD is equal to B times C. Well, in the next proportion, now you'll notice that things have been rearranged, but again, if I look at the cross products, okay, if I take, well, hold on. Let me use yellow to show we'd have AD again and B times C, okay? In the next proportion, when I cross multiply, I'd have AD times BC. And in the last one, if you cross multiply, we're going to have AD times BC. So there's many correct ways to write a proportion. You'll just need to remember that once you write that first ratio, you'll need to be consistent when you write the second one. All right, so that's a quick review of ratios and proportions. So now we're ready to talk about what this unit is going to be all about, and that is similar polygons. So just like we had a definition of congruent polygons, now we're going to have a definition of similar polygons. And that definition says the following: polygons that have the same shape but not necessarily the same size are polygons that we say are similar, okay? So definition of, sorry about that. Definition of similar polygons. Here's how we define it more rigorously. Okay, definition of a similar polygon. Polygons are similar if and only if their corresponding angles are congruent, okay, and the measures of their corresponding sides are proportional. Proportional, proportional. Now, note, the word proportional just means that we can write equal ratios, okay? So this is how similar polygons are different from congruent polygons. Our definition of congruent polygons would say corresponding angles are congruent and corresponding sides also are congruent. If the polygons are similar, we say that corresponding angles are congruent and their corresponding sides are proportional. So let's take a look at this example. We have two quadrilaterals, okay? In the diagram below, ABCD is similar to WXYZ. Notice they're the same shape, but they're different sizes. Now, we can show that these two polygons satisfy this definition of similar polygons because, first of all, their corresponding angles are congruent. You see one arc here on A, one arc on W, two on B and X, 3 arcs on C and Y, and 4 arcs on D and Z. So we can see that we have all pairs of angles are congruent. And then also, we can show that the corresponding sides are proportional, meaning we can write equal ratios. So, for example, let's take the ratio of AB to WX. Notice in your similarity statement here, AB would correspond to WX. AB is 15 and WX is 5. So I'm just going to write that below here, 15 over 5. Okay, let's compare that ratio to the ratio of BC to XY. Again, notice that BC are the middle two vertices and XY are the middle two vertices. So BC to XY is 12 to 4. Okay, and then CD to YZ, that's the last two vertices here, the last two vertices here. CD to YZ would be 21 to 7. And then last but not least, we have DA to ZW. DA to ZW, okay? DA to ZW is 18 to 6. Now, if you take all of those ratios and reduce them, they all reduce to 3 to 1, okay? So that shows us that the corresponding sides are proportional. We can write equal ratios. Okay, so let's use the definition of similar polygons to do this example. Find the indicated measures. Okay, we're given that quadrilateral NPQR, oh, by the way, this is the symbol for is similar to. I forgot to mention that when we were talking about the definition. So this little squiggle means similarity. So we have quadrilateral NPQR is similar to quadrilateral UVST. So let's fill in these blanks. Now, don't look at the picture, look at the similarity statement to see what angle N is congruent to. Remember, if we're told that these quadrilaterals are similar, then by definition, their corresponding angles are congruent. Angle N is mentioned first, so it would be congruent to angle U. Okay, and then angle P would be congruent to angle V. Angle V, all right. Angle Q would be congruent to angle S. And then finally, angle R would be congruent to angle T. angle T. All right, so that's the first part of the definition of similarity. We know that all four pairs of corresponding angles are congruent, okay? What also is true from the definition is that corresponding sides are proportional. So let's take a look at this ratio. We have NP to UV. So NP to UV, that would be this side to this side, is equal to the ratio of something to VS, okay? So to find out what to write in this blank, let's look at the similarity statement. VS are the middle two vertices named, so that means PQ would go in the numerator, okay? And that ratio would be equal to the ratio of QR to what? Well, let's see. QR is the last two vertices, so that would correspond to ST. And then finally, that's equal to the ratio of something to UT. Well, what would UT correspond to? That's the first and last vertex. UT would correspond to NR, which is this side. Okay, NR. So from the definition, we know which pairs of angles are congruent, and we know that all of these sides are proportional, the ratio of any two corresponding sides. Okay, part of the discussion of similarity is talking about scale factor. Scale factor is the ratio of the lengths of corresponding sides. So the ratio of the lengths of any two corresponding sides. Okay, so for example, in the diagram we're told that this big triangle ABC is similar to this little triangle XYZ. The scale factor, now, if we're going to talk, when we talk about scale factor, the order in which you mention it is important. So the scale factor of ABC to XYZ, that's the big triangle to the little triangle, is 6 to 3. Now, how did we get 6 to 3? Remember, the scale factor is the ratio of the lengths of any two corresponding sides. Well, 6 is AB. Now, wouldn't AB correspond to XY? That measure is 3. So the scale factor is 6 to 3, or of course that would reduce to 2. So that's if we talk about the scale factor of the big triangle to the little triangle. But if we turn it around and talk about the scale factor of the little triangle to the big triangle, then we would take 3 to 6. XY corresponds to AB. We'd take a side from the little triangle and put it over the side of the big triangle. So in that case, we would say the scale factor is 1/2. Okay, so let's take a look at an example. All right, this example says, determine if the triangles are similar. Show that corresponding angles are congruent and corresponding sides are proportional. That's how we would show that these triangles satisfy the definition of similarity, that corresponding angles are congruent and corresponding sides are proportional. If the triangles are similar, then we're going to write a similarity statement and identify the scale factor, okay? So let's start with the first part of the definition, showing that corresponding angles are congruent. Well, I see two pairs of angles marked congruent. You might remember from last semester we had a theorem called the third angles theorem that says if two angles of one triangle are congruent to two angles of the other triangle, then the third angles are going to have to be congruent. So I'm going to go ahead and put 3 arcs on P and 3 arcs on T. Okay, so let's start with the first part of our definition, showing that the corresponding angles are congruent. So we have angle N congruent to angle R. Angle N is congruent to angle R, okay? Then let's look at the ones that have 2 arcs. Angle Q would be congruent to angle S. Angle Q is congruent to angle S. And then lastly, angle P with 3 arcs is congruent to angle T with 3 arcs. So angle P is congruent to angle T. So we've shown that these two triangles satisfy the first part of the definition, that corresponding angles are congruent. Now we need to show that corresponding sides are proportional. So I'm going to take the biggest side of the first triangle. The biggest side of the first triangle looks like would be 15, and I'm going to compare that, write a ratio of that to the biggest side in the smaller triangle. Well, the biggest side in the smaller triangle is 12. So 15 to 12. Now let's go ahead and reduce 15 to 12. 15 to 12 reduces to 5/4, and you're going to see in a minute that it's going to be helpful if I even write that as a decimal. So that would be equal to 1.25, okay? So we've written a ratio of the big side of the big triangle to the big side of the little triangle. Now let's take the medium side of the big triangle and compare it to the medium side of the little triangle. So that would be let's see, 12.5 to 10. So 12.5 to 10, which would reduce, if you take 12.5 and divide it by 10, you're going to get 1.25. And then lastly, let's take the smallest side of the big triangle and compare it to the smallest side of the little triangle. So that would be 11.5 to the smallest side of the little triangle is 9.2. Now you'd probably have to grab a calculator to do this. But if you did, that would reduce to 1.25. So we can see that the corresponding sides are proportional. They're all equal to 1.25 when we take the ratio of any two corresponding sides. Okay, so we have satisfied the definition. We've shown that corresponding angles are congruent and corresponding sides are proportional. So now we're ready to say, yes, these two triangles are similar, and we can write our similarity statement. So we've already have the similarity statement started, NPQ, so that's going to dictate how we name this one. Remember, N with one arc correspond to R, so we're going to call this triangle R, and then P that had 3 arcs corresponds to T that has 3 arcs, and then finally that leaves Q corresponding to S. Okay? And then our scale factor, remember, is the ratio of any two corresponding sides. Now, I'm going to go ahead and list the scale factor as the big triangle to the small triangle, since that's how we wrote our similarity statement. So the ratio of any big side to the corresponding big side of the other triangle, or medium or small, all of them reduce to, we can either say we can either say that scale factor is 5/4, or we can say it's 1.25. So now let's use the definition of similarity to solve a problem. In this example, it says find x and y given that triangle JLM is similar to triangle QST. The similarity statement is going to help us a lot. So we need to find x and we need to find y. So let's start with finding x. So what I'm going to do is I'm going to take a ratio, I'm going to write a proportion. So I'm going to compare LM to, what would LM correspond to? Well, it would correspond to ST. So let's write that ratio of LM. We're going to take LM and compare it to ST. And then I'm going to compare that to the ratio of any other two corresponding sides. So I need to use some that actually are labeled. So let's see. Let's try JL. JL, let's see. Let's go ahead and write another ratio of corresponding sides. How about we'll take side JM that measures 4, and J and M then would correspond to QT, which measures 2. So let's compare that to JM. Whoops, we're in the wrong spot. Fix that. JM to QT. All right, so let's go back and fill in our proportion. So remember, LM is 6x minus 3. So 6x minus 3 to ST, which is 3, is equal to JM, which is 4, to QT, which is 2. All right, so now we have a proportion that we can cross multiply and solve. So if I cross multiply, remember there's a binomial here, so let's put parentheses around it. And when I cross multiply, I'm going to have to distribute this 2 to both of these terms. So that would be, let's see, 12x minus 6 is equal to, when I cross multiply the other way, I get 3 times 4 is 12. Okay, and then I'm running out of space, so I'm going to run over here. Okay, when we add 6 to both sides, then we'd get 12x is equal to 18. And so x is equal to 18/12, and that, of course, reduces if there's a common factor of 6, so that would reduce to 3/2. So we have found our x. Let's now write a second proportion to find y. So I'm going to write a different kind of proportion, because remember, there's so many correct ways to write proportions. This time, to find y, I'm going to compare, I'm going to take the ratio of any two sides of the first triangle. So let's say we took JL to JM. So let me write that ratio, JL to JM, and then let's compare that to the ratio of the corresponding sides in the other triangle. Well, JL would correspond to QS. So and then JM JM, that's the first and last, would correspond to QT. Correspond to QT. Okay, so let's go back and fill in the expressions. JL is 3y minus 2. JM is 4. And then QS is 5. And QT is 2. All right, so when we cross multiply then, we would get 6y minus 4 equals 20. So 6y equals 24, and y is 4. Okay, so I just want to mention that there are many, many correct proportions that you could have written, and you'd have gotten these same two answers, okay? Because remember those properties we said, the cross products are always going to be the same, so there were many correct ways you could have written these proportions. Okay, so let's end with a theorem. This theorem says if two polygons are similar, then their perimeters, that's the distance around the outside, their perimeters are proportional to the scale factor between them. In other words, the ratio of the perimeters is equal to the ratio of any two corresponding sides. So for example, if we have these two quadrilaterals that are similar, remember that was our similarity symbol, then if I add up all these sides, that would be the perimeter, the distance around this first polygon or quadrilateral. So the ratio of their perimeters is equal to the ratio of any two corresponding sides. Okay, so let's use that theorem to solve this problem. Given that MNPQ is similar to XYZW, find the scale factor and the perimeter of each polygon. Okay, so to find the scale factor, I just need to take the ratio of any two corresponding sides. So I notice in this first triangle, quadrilateral, the only side I know is WX. So what would WX correspond to? WX would correspond to QM. So let's write that ratio to get our scale factor. WX would correspond to QM. Or if I put in those values, WX is 4 and QM is 8. So our scale factor is 1/2. Now, the theorem tells us that the scale factor is equal to the ratio of the perimeters. So in other words, I can say that that ratio of 1 to 2, now notice I've taken the ratio of a side of the smaller triangle to the side of the bigger triangle, that's going to be equal to the ratio of the perimeters. Now, I don't know the perimeter of the small triangle, so I'm just going to call it X. I can figure out the perimeter of the, did I call it a triangle? Sorry, quadrilateral. I can find the perimeter of this big one just by adding these four sides. 9 plus 10 plus 7 plus 8 totals 34. So you can see I've written a proportion that shows that the scale factor, the ratio of any two sides, is equal to the ratio of their perimeters. So now I can cross multiply and solve. So I would get 2x is equal to 34, so x is equal to 17. So we can finish this off and say, we were asked to find the perimeter of each polygon. So we can say that the perimeter of the smaller quadrilateral, WXYZ, is 17, and the perimeter of the larger quadrilateral, XYZW, is 34. All right, so if you have any questions about these notes, be sure and ask me in class, and I will see you then.